Hello everyone, Liam Watley here and welcome to the AI Landscape. This video is a foundational part of your understanding of the space as a whole and really the context in which we're going to be building these businesses. So we're going to be covering a few key things, like firstly, what is artificial intelligence, getting a clear idea of the definition and what the technology really is and what it's trying to do. Secondly, we'll be going over the different AI types and terminology, giving you a clear understanding of the landscape of the AI space and the different disciplines and studies within it. And finally, we'll do the Gen AI providers, giving a breakdown of the different players in the space and their offering. All right, we can get started. So I've got most of this introduction out of the way, but just to recap, in this video, we'll break down the world of artificial intelligence into its different areas, explaining each one and how they are connected. We'll also break down the biggest players in the field and where they stand in the big picture. Now, while this program is primarily focused on selling Gen AI solutions, it has been greatly beneficial, at least in my journey, to be familiar with the other kinds of artificial intelligence to provide a broader perspective on the space as a whole. So first things first, what is artificial intelligence or AI? At its simplest, artificial intelligence is about creating machines that can perform tasks which require human intelligence. So here we have a little definition for you. AI are machines that can perform tasks which require human intelligence. Now, there are a bunch of different definitions for it, but this is where I want you to start, and that we are trying to replicate human intelligence so that we can create different systems and programs with it. In order to replicate human intelligence, we need to replicate the sort of complex functions that our brains are able to do. So as intelligence beings, humans can perform a wide range of complex functions, including firstly problem solving, the ability to solve complex problems or simple problems in an efficient manner, understanding of natural language, so comprehending and interpreting human language as it is written or spoken. We can recognize patterns and images, so identifying patterns, sequences, or images and making sense of them. We're good at making decisions, or some of us at least, choosing the best course of action based on data and past experiences, so current data and also past experiences. And finally, learning from our experiences, improving performance or gaining new knowledge without being explicitly programmed for every task. Now, when you break it down like this, you really start to get a feel for just how impressive and amazing the human brain is and what we're able to do as intelligent beings. Because as you'll see, and as I'm sure you've probably found out from some of your tinkering already, getting machines to do this kind of thing is no small task. It's no mean feat to be able to achieve this in a computer program. So artificial intelligence itself is not a monolithic technology. It's not one thing. Nowadays, everyone is calling this and that AI, like everything is suddenly AI, and really it's all focused around this LLM stuff. But it's not just one monolithic technology. It's actually an expansive field that covers any effort to create machines capable of intelligent behavior. So while you may think AI is just ChatGPT, it's actually a lot broader than that, and it has been around for, technically around 50, 70 years. So within this, there's been a lot of different methodologies, technologies, and approaches that we're going to cover in this video. And all of these that we're going to cover are aimed at mimicking or surpassing human cognitive function. But what makes artificial intelligence systems so powerful is not only the potential to, as mentioned above, surpass human intelligence, but also the ability of these systems to have such intelligence on demand or on tap. And therefore, we can deploy it at a huge scale. So once an AI system is capable of performing a human task, scaling up the usage of that intelligence to millions or billions of users is a relatively trivial task. ChatGPT is an obvious example of this. This potential for deploying human-level or greater intelligence at enormous scale is, in my opinion, the most exciting part of AI due to its impact on the advancement of and well-being of humanity as a whole. So this is really what I want to get drilled into you guys' head just at the start, is that AI is about creating these artificially intelligent machines that can do tasks that humans would normally have to do. And the key part of that is that once you're able to do it and achieve a system that can replace a human in a task, we can then scale that up to millions or billions of users, as we have the example of ChatGPT. Once they've cracked the code of how to create this artificially intelligent LLM-based assistant, they're able to scale that up, scale their infrastructure up and release that to billions of people. They've probably reached billions of people by now, if you added up all the users, but hundreds of millions of people at least have suddenly got access to this artificial intelligence on tap. Now, if you tried to create a team of humans that was large enough to essentially do what ChatGPT has done and answer questions on demand for hundreds of millions of people, the size of the team would just be completely impossible to achieve. I mean, it's just simply not possible to have this level of intelligence, which is really with ChatGPT, you've got an expert in basically all fields now at your fingertips. We would never be able to achieve that, even economically. You can't possibly think of affording an expert for every person on tap, on demand, 24/7. So that's really the magic, and that's what I want you to understand from this part, is that we're trying to replace human intelligence. Once we do that, we've really cracked the code and can scale that up. And that's what we try to do as AI automation agency owners. So a few examples of real-world AI systems. Prior to ChatGPT, humans have been very successful at creating AI systems for various use cases. The following examples highlight the ability of AI to replicate the human-level intelligence required to perform tasks of varying complexity. So just a couple quick examples here. We have things like resume screening. Prior to AI, recruiters will have to manually review each resume to determine the candidate's suitability, a time-consuming and biased process. But after, we can build AI systems that automatically analyze these resumes, extract relevant info, and rank candidates based on job requirements, saving time and reducing bias. And then we have things like diagnostic healthcare tools. So before we had AI systems, medical professionals would have to manually analyze medical images, patient data, and genetic information, relying on their training and experience to diagnose diseases and recommend treatment. So it was fully manual process. We wouldn't have any computers in the mix trying to analyze these things. It would just be a medical profession and their understanding and the years and years of experience and training. But now we have AI algorithms that have been developed to automatically analyze medical images, patient data, and genetic information to assist in diagnosing diseases, recommending treatments, and therefore enhancing accuracy and efficiency. And finally, a financial fraud detection. Prior to AI systems, human analysts were required to monitor financial transactions manually, needing extensive training to spot inconsistencies and patterns indicative of fraudulent activities. And now we have AI systems that have been implemented to monitor these financial transactions in real time, automatically identifying and preventing fraudulent activities by analyzing these patterns, etc. So you get the idea. Before, humans would have to be involved in basically all of these tasks. But once we were able to create an AI system, whether it's through LLMs in this case likely, or through more traditional AI, where we're using AI algorithms and machine learning and things like this, which we're about to learn about, we've been doing this for a while now. But the key is that you're able to go from a human task to an AI or a computer that's able to do the task for us. I mean, it's a lot easier to scale that implementation. So jumping now into the AI landscape itself. So since the coining of the term artificial intelligence in 1956, efforts to craft systems mimicking human intelligence have led to the development of numerous subfields, each with unique focuses and applications. Here's a broader look into these areas, including key concepts and terminologies. So firstly, artificial intelligence is the umbrella term that encompasses various methods that enable machines to execute tasks, usually requiring human intelligence. For example, ChatGPT utilizes multiple AI techniques to comprehend and generate human language, showcasing the integration of different AI subfields to create sophisticated language models. So artificial intelligence, first thing, is the umbrella term that encompasses all of the other stuff we're about to cover. Then machine learning, something you may be interested in. Well, you may have heard before. It's been used for a lot of different applications. It's been around for a while. And some of you may have even dabbled in it before coming into this program. But machine learning is a subset of AI, which equips computers to learn from data patterns and make predictions without explicit programming. So this is really the key part of what makes machine learning so special and so much more powerful than many forms of traditional software development. Within machine learning, we now have all these different types of learning methods. Firstly, supervised, which is training models on labeled data, helping them map input to outputs. Unsupervised learning, which is focused on discovering hidden patterns in unlabeled data. Reinforcement learning, which involves an agent learning to make decisions to maximize rewards in a given environment. Deep learning, a machine learning subset that uses artificial neural networks to learn data's hierarchical representations. Computer vision, a subfield of AI which aims at teaching machines to interpret visual data as humans do, really. NLP, or natural language processing, is enabling machines to process and understand human language, which is a lot harder than you'd think, as you're going to see in later videos within this module. And finally, we have generative AI, which is again a subfield of machine learning. It's a generative AI like GPT models generate new content from learned data patterns, differing from discriminative models used in classification and prediction tasks. So we're going to cover all of these in this next section. And here's a handy diagram that we've got for you to understand how all of these different areas are interrelated. We have artificial intelligence as this umbrella term, which encompasses all of these different types within. And then we have machine learning, which basically eats up everything else as well. Basically all of the stuff that you're going to be dealing with is going to be based on some kind of machine learning techniques. And here we have things like natural language processing, and here we have language models. So they overlap between deep learning, unsupervised learning, and here natural language processing, where it fits into transformers and large language models. So computer vision, etc., reinforcement learning, all of these different disciplines fit into the artificial intelligence space in some way, but they all have interesting sort of overlaps between each other. So for the rest of this video, we're going to be breaking down these different types and giving you a deeper understanding of how they fit together. So types and terminology, starting off with machine learning. Machine learning is a subfield of AI that enables computers to learn patterns and make prediction from data without being explicitly programmed. So there's four main approaches: supervised, unsupervised learning, deep learning, and reinforcement learning. What I just covered before, which is the exciting ability of machine learning, is that it can make predictions or decisions on things it wasn't explicitly trained to handle, which contrasts sharply with traditional computing, which requires very specific instructions to perform any task. Traditional systems can't deal with unknowns or make predictions outside their program capabilities, limiting their adaptability and intelligence. So with machine learning, as we'll see like in this example, if you provide it with the data and you're able to train it and create this model, it is essentially able to have new inputs provided to it and also be able to come to a conclusion or make a decision based off that. So it is really the opening up of computing from strictly, I write this program that does this, and this is the outcome. I've manually programmed in all of the functionality, to let's just funnel a ton of data through one of these models. And now it's able to, based off the learnings and the training that it does on that data, it is then able to handle new inputs that it has never seen before and also come to valuable and correct conclusions, which is a massive leap forward in computing. The fact that you can now have these things which can do things that they were not explicitly programmed to do, which is really the magic here. So an example of machine learning is things like recommendation systems. So Netflix and Amazon, they use recommendation systems that are built with machine learning to identify content you'd be interested in watching. So they analyze your past behavior and preferences, along with data from similar users, to predict and recommend movies or products you might like. This is done even though the systems were never specifically programmed with those preferences. So they take in your past behavior and preferences, and then data from similar users as well, and it's passed through this machine learning model that they've trained, and then it's able to recommend things that you'll be likely to, or highly likely to want to watch or purchase. So this ability to adapt and learn from data to predict and act on things they weren't explicitly trained to do shows how machines can now make accurate predictions without explicit instructions, marking a significant leap forward in making machines smarter and more autonomous. So machine learning, massive leap forward in computing, and the fact that it can deal with situations which it wasn't explicitly programmed to do. Then we have supervised learning, which operates by using labeled data sets to train the model. So this is, again, a subset of machine learning. If we go up here, machine learning is another umbrella term, which basically encompasses a lot of the stuff we're going to be covering or you'll be running into in the space. But supervised learning is the first one of these training methods within the machine learning space. So supervised learning operates by using labeled data sets to train a model, enabling it to understand the relationship between input and output labels. So this is really the key thing here, understanding the relationship between input and output labels. If it can understand this relationship, then if you provide it with a set of inputs, it can theoretically, if you've trained it and if you've got a good data set, therefore predict the output label for that input data. So this process is akin to teaching a child with examples. By showing a child what the correct answer looks like over and over again, they learn to recognize the patterns and make predictions. So here's an example to illustrate this. Predicting house prices, one of my favorite ones, and what I initially was learning when I was learning Python and machine learning. This is one of the ones that I was working on within the courses I did, and this has really helped me to understand how these systems work. For the data set of this, we're going to have a detailed spreadsheet with columns of various housing attributes, e.g. the size of the house, the number of bedrooms, number of bathrooms, etc. And each of these is a house, right? So each row here within the spreadsheet is a house with a location, a size, number of bedrooms, etc. And the final column, aka the label column, which we're trying to predict, has the price of the house. So this model that we're trying to do is predicting the house prices. And we need to have all of this data. And firstly, in this training phase, we will have a selection of or a subset of the data set, which actually has the price or the label. And from this, it's going to be able to learn the relationships between these input data fields and the output as well. So in the training phase, the supervised learning model examines the data set, identifying patterns and relationships between the house attributes, like the size, the bedrooms, etc., and the prices in the label column. For instance, it might learn that larger houses in desirable locations are pricier, or that an extra bedroom increases value. So we fundamentally know this as humans. It's pretty straightforward to us to go, okay, well, we have bigger house, more bedrooms, nice area. But these machines and these models have no understanding of this. So we need to provide them with as many examples as we can for them to learn their relationships between, okay, this was 3.3 million, it's got 5 bedrooms. Okay, this one's much cheaper than that, and it's got 1 bathroom and 1 bedroom. Okay, carry up a size, yep, okay, bedroom. Then with enough examples, it can start to learn these relationships. Then we go through the learning process, which involves adjusting the model parameters to minimize the difference between the predicted prices and the actual prices in the data set. So it can predict examples. This is my hometown in New Zealand. It can predict this, and we also have, ideally we have the real answer as well, so we can compare the two, and that's how you're able to train these models. But through this learning process, it'll understand the relationships between these different data, between the inputs and the outputs. And then finally, after training, and we've gone through the process of predicting and then comparing it with the actual answer, that's how it can work back and forth and go through this learning process and adjusting the model's parameters. So it'll predict it, see what the difference between the predicted answer and the actual answer, and then go back and modify the parameters within the model to minimize the difference between the predicted price and the actual prices. So once it's got that difference as low as possible, then it's been trained to the specific use case and it's ready to be used for prediction. So after training, the model can predict the price of a new house based on these attributes. Inputting details such as a size, location, and number of bedrooms allows the model to apply learned patterns to estimate the house's price. So then we have, say this was the training data, if you can see here. Training data are these green rows, which we could use because it's got the label. But these ones we can then start to predict the actual prices with. So we could pass in this row of data, and it would predict the price here. So this is what supervised learning looks like in action. And once we have this model prepared and trained properly, we can then be passing in data and it will be predicting the output label here. So supervised learning thus empowers models to make informed predictions and decisions from historical data, serving as a cornerstone for numerous practical applications. So this is a really key and fundamental part of machine learning that you need to understand. It's the most straightforward one to do. You can go into Kaggle and whip up one of these yourself and watch a very quick machine learning tutorial and be able to train a model that is able to do predictions like this. It's quite satisfying to do, and I urge all of you guys, if you're interested in this sort of stuff, to go and have a play around with it, or at least watch some tutorials on it, because it is quite cool that you can just create this model that you can throw data at and it's going to give you the labeled out. And also the training and optimizing process can be quite cool to do as well. Then we have unsupervised learning, which again is another subset of machine learning. But this refers to a training approach designed to uncover hidden patterns or structures in unlabeled data. So here we have labeled data, where we have some kind of label column, which is what we're trying to predict. But in unsupervised learning, there is no labeled data. So without the need for predefined output labels, making it ideal for exploratory data analysis, uncovering hidden correlations, or automatic classification. So a good example of this is segmenting customers. You might have a data set which contains various customer attributes such as age, income, spending habits, social media activity, etc. This obviously lacks some kind of specific label that we're trying to aim towards or categorizing the customers with. It's just a whole bunch of seemingly unrelated data that we can then use a unsupervised learning process to create a model that allows us to see things like this and get clusters. So in the analysis phase, the unsupervised learning model processes this data to find the natural groupings or clusters among the customers. For instance, it might identify clusters based on spending habits or preferred communication channels. So in this example here, you can see this is what our data would look like initially, but through unsupervised learning, we can train a model that will be able to cluster and recognize hidden patterns in this data based off things like age, income, spending habits, etc. In the discovery process, the model will iteratively adjust its parameters to better cluster the data. This process often involves techniques like k-means clustering or hierarchical clustering that organize data into groups with similar characteristics. A little bit harder to understand in some cases. It's really dependent on the use case, but this can be very helpful for identifying hidden patterns that, purely because these models can see and be trained on such large data sets, they can identify patterns that us as humans simply can't do. So still very important and used really a lot throughout the world. Then in the application, once clusters are identified, the company can then tailor its marketing strategies to each specific group, improving customer engagement and sales. For example, a cluster identified as high income, low spending might be targeted with luxury product campaigns that emphasize value and exclusivity. So unsupervised learning therefore provides a powerful tool for understanding complex datasets and extracting valuable insights without pre-existing labels. So great, there's always a time and a place for using each of these methods. Next, we have reinforcement learning. Reinforcement learning is a powerful method where a model learns to make decisions by interacting with its environment, aiming to maximize rewards over time. So it's similar to training a pet. Rewards are given for good behavior, teaching the agent to repeat those actions, while penalties are given for mistakes in order to discourage them. So an example here is teaching a robot to navigate a maze, a complex maze with the obstacles and rewards scattered at various points, and a final goal. So the robot is starting here, wants to get to here, and throughout the process, it's going to bump into walls, and it's going to get negative rewards. And there's going to be positive rewards that tell the model, hey, look, this is the right way. Keep doing stuff like this and incentivizing it to keep doing it. Then we have the learning process where the robot or the agent will start with random movement. So it might go boof and bump into the wall there and into there. Each time it hits the wall, it's going to have a negative reward. So it's going to go, okay, I went this way and I hit the wall. I shouldn't go that way again. So just by trial and error, we'll keep going until it goes, oh, I've got a positive reward here. I should keep following this route and doing that again and again. So each time it hits an obstacle, it will receive a penalty or a negative reward, and reaching a reward or the goal will yield a positive reward. Then we have the adaptation phase, which is through trial and error. The robot will analyze the outcomes of its actions, whether it ran into a wall or got a reward token here. It learns the optimal path for avoiding these obstacles and to maximize the collection of these rewards. So say we had a little reward token here, it might even go down here and collect the reward and then come back up here purely through trial and error, because it might go down and hit the wall there, therefore get the negative reward, but it's going to turn around and try to maximize the collection of these rewards. And it will adjust its strategy based on the feedback received from the environment. And finally, after sufficient training, the robot can navigate any new maze it encounters efficiently by applying the strategies it learned to achieve the goal with minimum penalties. So reinforcement learning thus enables models to learn optimal behavior for self-improvement, adapting to new challenges intelligently. This approach is fundamental for achieving autonomy in machines, allowing them to perform complex tasks without explicit instructions. So very important learning and training technique that's actually used heavily in ChatGPT in order to get it to do the things that we want it to do and give the kind of outputs that are favorable to humans and the people using them. So we'll be covering this more in a later module. Next, we have deep learning. So deep learning is a branch of machine learning which employs multi-layered artificial neural networks to handle complex data patterns effectively, mimicking the incredibly advanced and powerful architecture of the human brain. So while we're still very far off achieving the brain's level of intelligence, these networks do excel at modeling the intricate relationships by learning from vast data sets. This significantly improves tasks like image and speech recognition and natural language processing by developing rich, hierarchical representations of the data, making them uniquely suited for complex information. Complex information like images, where you've got so many different inputs and pixels that you need to analyze. Natural language, where there could be thousands of words in a document. When we need to understand these more complex data types that are not just like a spreadsheet, like we provided before for the supervised learning example, there is really complex data that we need to understand. Deep learning is the technique that we've gone with, which is based on these artificial neural networks. So in the next video of this module, LLM theory, we'll dive deep into deep learning and neural networks as well. So some popular applications for deep learning include image classification and object detection, speech recognition and natural language processing, recommendation systems for personalized content, and predictive modeling for various industries like healthcare and finance. So easy and typical example for deep learning here is enhancing image recognition. So being able to provide a vast collection of images with hand-drawn numbers on it, and then having the deep learning model be able to tell you or predict what the number is in the image. In the training phase, a deep neural network, like a convolutional neural network or CNN, is trained on a data set of these hand-drawn images. It learns to recognize patterns and features at multiple levels of abstraction, from basic shapes at lower layers to intricate details at high layers. I don't want to get too in-depth here because we're going to cover it in LLM theory, but there are different layers within this, and each layer within the network can be used to identify or pluck out certain aspects. So it could be this top part of the three, and then this curvy bit at the bottom goes, okay, those two, okay, if I put those all together, that's most like the three examples that I've seen. So you do train this in a supervised way where you provide it with, here's an image and here's the ideal output, And after we run it through this enough times, it can go through this training phase and change the weights and the biases within the network. And then it's going to be able to predict this on things that we haven't necessarily shown it before. So getting a little bit in the weeds there, but we've got a lot to cover in LLM theory. Then we have what's called feature extraction. So as the network processes these images, it identifies and extracts features, e.g. the top part of the three, which are important for classifications, such as edges of the initial layers, followed by more complex shapes and eventually specific characters unique to each category. Finally, we have the application. So after training, the network can classify new and unseen images with high accuracy. For instance, it can differentiate between a cat and a dog in new photos if you're doing one for animal recognition, based on the hierarchical features learned during that training. So here, for us with the image example, we'd be able to throw different images that it had never seen before at it, and it would be able to accurately predict it based on the training data and basically the configuration of the network that it's gained from the training process. So deep learning thus offers a powerful framework for computers to mimic human level understanding in tasks like visual recognition, making significant strides towards advanced AI applications without needing explicitly programmed for every single task. So again, by providing it with enough training data and setting up this neural network with the correct weights and biases, as you'll learn later, we can then throw new data at it and it's going to be able to predict it as well. But it's particularly important for this more complex data like images and speech, etc. Then we have computer vision. Just as deep learning revolutionized how machines handle complex data, computer vision is transforming the way that computers perceive and understand visual information from our world. This field of AI focuses on teaching machines to interpret, process, and analyze images and videos similarly to how we do it as humans, but with added advantage of scalability and precision beyond human capability. So going back to the whole reason we create AI systems, right? We're trying to mimic human level intelligence and abilities, in this case, of seeing and perceiving things through our eyes and then being able to make decisions and communicate stuff based off the back of that. In this field, it's really trying to achieve that human level or even superhuman, so we can get even better and more precise analysis of images and video. But once we've got that, we can then scale it far more than if we were trying to create a human team of 10,000 people to look at these images. That's really the excitement and the interest in computer vision, is the scalability of it once we've got it figured out. So key applications of computer vision include image classification, automatically categorizing images into different groups, object detection, pinpointing objects within images and determining their boundaries, semantic segmentation, breaking down images pixel by pixel to classify each part of the image according to the object it belongs to. And finally, facial recognition as well. So identifying or verifying a person's identity based on their facial features. This stuff here, it took us a long time to get computers that could do that. We can now obviously do it with our iPhones and Androids and whatever phone you've got. You can open it and unlock the phone with your face. But humans and children can do that from a very young age. It just shows how complex and advanced the human brain is, even at a young age, because facial recognition was no easy task for us to figure out. Example here, we have advanced autonomous driving. So the data set would be, we're training a computer vision model based on thousands of hours of video footage from vehicle mounted cameras, capturing diverse driving environments and conditions. So using deep learning models like CNNs to analyze this footage, the models can learn to detect and classify various elements crucial for safe driving, such as road signs, pedestrians, and other vehicles across multiple layers of complexity. So here we have an input. And the network, the computer vision model is based on deep learning. It's built on a neural network, as you can see here. So we can pass in inputs, and all of these different pixels of this image can be passed into the input layer, which you're going to learn more about later. But they can get passed into the input layer, and then outside, on the other side, we can have a label or a classification where it's, okay, in this image there is a sign, or there is a car, etc. And then we need to do actions based off the back of this. There's feature extraction again, as we have with the deep learning example before. The trained network identifies and extracts key features from the visual data, starting with simple shapes and textures to complex objects and scenarios, essential for making split-second driving decisions. And after the training, these AI-powered systems enable autonomous vehicles to navigate safely by accurately identifying and responding to dynamic road conditions and obstacles, showcasing a significant leap towards fully autonomous driving. So computer vision models powered by deep learning are moving us towards truly smart machines with the ability to see and interpret their surroundings. And more importantly, these machines can analyze visuals on a scale with precision far beyond human capability when done correctly. With models like GPT-4o, the once complex field of computer vision is now accessible to many. So for a long time, computer vision was very tech heavy, like you're having to train these neural networks yourself or plug them in and use Python to be able to run them and pass images into them. It was kind of a gated community for people who knew how to code. But now with things like GPT-4o and the advancements in computer vision and the access to it through things like ChatGPT, we now have a much easier access for anyone who wants to get into building computer vision-based solutions. Then we have natural language processing, or NLP. So natural language processing, or NLP, not to be confused with neuro-linguistic programming, which is, it's got the same letters for it, NLP, is a branch of artificial intelligence that allows computers to understand, interpret, and generate human language. NLP combines a variety of techniques to achieve its aims. Now, this is a really important one to get right. The primary goal of NLP is to break down the barriers that hinder seamless communication between humans and computers, enabling machines to process text and speech as effortlessly as we do. So this is something that even I struggled to really wrap my head around. I was like, NLP, like, who really cares? It's sure, I mean, ChatGPT kind of does it. These models are already figured out. It didn't seem that sexy or exciting to me, but when you frame it like this, and that the primary goal of NLP is to break down the barriers that hinder seamless communication between humans and computers. So the communication between man and machine is really what natural language processing is all about. And whether that's going to be us speaking or typing, or even sometime in the future, just thinking, that's that human to computer interface and the way that we communicate with each other. And until we had these amazing language models and things like ChatGPT, it was hard for computers to understand what we wanted to do through natural language. And that's why it's really so much more exciting when I understood this frame. And then that is a spectrum, right, of human to machine interaction. And NLP is really focused on making that as seamless as possible, because instead of us having to, like, typing into a computer and me having to write all the stuff out, and you having to operate your computer manually, is really inefficient. Ideally, you'd just be able to think and it would do what you needed it to do. You could make a call just by thinking about something, but we don't have the means to do that, or until recently, we didn't have an efficient means of communicating with computers. We'd have to click and go up here and press buttons, but now we have things like ChatGPT and language models that can better understand what we're saying and what we want to do, and allows computers to understand it better. So recent breakthroughs in NLP using deep learning techniques are responsible for the development of successful technologies such as chatbots and large language models like ChatGPT, which have completely revolutionized the way that humans and computers interact, as I've just said. So key applications for NLP include sentiment analysis, determining the sentiment conveyed in text; machine translation, so converting one language to another; speech recognition, transcribing spoken words into written text; text summarization, condensing large bodies of text into concise summaries; and named entity recognition, so identifying and classifying named entities such as people, organizations, locations, dates, quantities, etc., which is a pretty handy one too. So an example of an NLP system in action could be a sentiment classification system for e-commerce. So say an e-commerce brand wants to track customer sentiment across Facebook and Instagram ad comments. Now the challenge with this is that they have thousands of comments, so manually determining the sentiment as positive, negative, neutral behind each will just not be feasible. They need to have virtual assistants going through and grading all of them and tracking them in a spreadsheet. It's just not realistic. So the solution could be implementing a sentiment classification model that enables the brand to automatically analyze the sentiment of the comments and assign a sentiment score to gauge the overall customer perception of the ad. So zoom in here, I've got a nice little diagram. Say I ran this ad and then I got all these comments on it. Very helpful. Hey, cool too, this is bad. We can run all of these comments through our classifier model, our sentiment classification model. And it's going to determine which are positive, which are negative, and which are neutral. And then we could get this new, what would you call it? A new score, or a new metric, sorry, of the sentiment score of the ad. So now we could be looking at more interesting data for us, as say if I was the marketing agency who was running the ad account. I could go, okay, well, the sentiment score on this ad seems to be way high and it's also performing very well. So maybe this is a case of we've really struck the angle right and it's resonating with a lot of people because we've got such a high sentiment score. So this could be an interesting way of adding another metric to your ads data to determine whether or not an ad was performing well. So the outcome, this approach provides the e-commerce brand with a new performance metric, the sentiment score, offering an immediate insight into customer satisfaction and areas for marketing message adjustment. So if it's a negative sentiment, you might want to turn it off, or you might want to modify the angle of it, etc. It showcases the power of NLP in extracting valuable insights from large volumes of social media data, aiding in strategic decision making. The cool thing about NLP is that with these language models we have now, we can analyze and do things with large amounts of text because text has so many different ways that you can write something, right? We could never really write a computer program that would be able to handle any text you throw at it, because we always had to strictly define, okay, this is what it does, these are the functionality of the program, etc. But now with these models, we can throw stuff at it and it doesn't have to be in any strict format. It can just be, do this with this text that comes in, and we can pass anything to it, which is really the NLP is everything that we do in the space, really. So it's important to understand it. Then finally, we have generative AI, and the G in GPT stands for generative. So generative pre-trained transformer. But generative AI is a key concept that distinguishes GPT and other generative models from non-generative AI models. So the main difference is non-generative or discriminative models make decisions or predictions based on the input. So going back to our example here, they get given a set of input and they make a prediction, or they make a decision. This might be maybe a 0 or a 1, a binary, or in this case, a prediction. When it comes to our generative AI, generative models create new content based on their training data. So we provide, yes, some kind of input, which is in our case, the prompt, but it's generating new content based on what it was trained on. So for example, a discriminative model trained to classify emails as spam or not spam will analyze an email's content and produce a predefined output. So this is really key. Either spam or not spam. It has been trained to output one or the other. In contrast, a generative model trained to write emails will create a unique original email based off a given prompt. So here, you see the email comes in to the discriminative model. It's been trained to only output as a 1 or a 0. So as a spam or not spam. And then that would determine which folder it ended up in. But for a generative model, we have a prompt. We pass it to the generative model, and it generates a new and in often cases unique output based off this, using the training data it was provided with. So the evolution of generative AI, or Gen AI, has been marked by several milestones. In 2014, we had Generative Adversarial Networks, or GANs, by Ian Goodfellow and colleagues. So this is quite a while ago now, nearly 10 years. In 2017, we had the development of Transformers by Google, which is a massive leap forward for the NLP space, revolutionizing natural language processing, NLP, with its self-attention mechanism, which we're going to go into more in the next video in this module. Then in 2022, we had the release of ChatGPT, which made generative AI accessible to consumers through an easy-to-use chatbot-style application. And with the release of ChatGPT, it marked a turning point for generative AI, sparking an explosion of interest in its potential. As the world's brightest minds rush into the space, like you reading this and watching this video, the technology continues to evolve rapidly, creating lucrative opportunities for AI agency owners to sell AI solutions to businesses that have been left behind or are at risk of being left behind. So that's really our opportunity. Everyone's rushing into the space since the release of ChatGPT because it's so clear that these things are the future. So, and just before we go any further, I do want to briefly touch on generative AI naming conventions and types. Just as you run into these out in the wild when you're building your solutions, it's important to understand this formula here of how these generative AI models are named based on the input and output modalities. So it's in the format of input to output. Here we have the formula, input type to output type. So text to text, like ChatGPT, you provide text in and it gives you text out. Text to image, like DALL-E or Midjourney, you provide text to it and provides an image out. Text to speech, speech to text, image to text, etc. So you get the idea. This is the format. Text to video, things like Sora, and text to 3D, like some of the models that are out there at the moment. So just very quick touch on these, as you're going to see it everywhere. But understanding that, say you're doing a speech to text is a transcription, right? So you pass in a speech or audio. Technically, you could have this as audio, but in this case, it is an audio file that contains speech. So you pass in the audio file and it's going to generate or output the text. This is essentially just showing a transmutation of the data type, right? So it's going from text to text or text to image. This is really the magic and where the value in AI is created a lot of the time, as we're going to go into later. But you're transforming data from one form to another. So just a quick touch on that. Then we can get into the last section of this video, which is Gen AI providers. So since ChatGPT's launch in late 2022, the race is on among entrepreneurs like you and I, but also the tech CEOs around the world for a share of this massive and booming generative AI market. So driven by the potentially huge rewards and partly due to the pressure of these big companies having to have a clear AI strategy, the world's tech giants are all vying for dominance in the generative AI space. But thankfully for us, competition is a force for good, which drives down the, at times, astronomical cost of LLM usage. For those of you who've used GPT-4 when it first came out, it was extremely expensive. But providing new and innovative products that push the space forward and providing us with new vendor options for our AI solutions. So competition is great for us, really, at the end of the day. It forces them to make things cheaper so that they stay competitive. We get new options to build on, and it's good for us at the end of the day. And we have an evolutionary tree here showing, I won't get into this stuff too much, decoder only, encoder, decoder, encoder only, etc. But you can see that the current language models that we have are on a distinct branch. We have GPT-1, GPT-2, etc. And we go into this more within the LLM history module. So each provider has its own unique story and their own unique position in the market as well. So in this section, we'll be digging into the background and products for the biggest names in the space so that you have a good lay of the land, AI landscape, right? When it comes to choosing the tools you use for the jobs that you do. Firstly, of course, we have OpenAI, originally founded as a philanthropic effort, so as a non-profit, to avoid the potential concentration of AGI within a handful of large tech companies such as Google, Facebook, and Microsoft. OpenAI has become the world's leader in generative AI. Its mission is to ensure that artificial general intelligence benefits all of humanity. Put that on italics because we're not too sure if they're sticking to that right now. While its position as a purely research-based and philanthropic endeavor has shifted considerably from its original roots, it's now a for-profit company backed by Microsoft. OpenAI continues to produce high-quality products and research at an astonishing rate. So they still have a massive research department and are really pushing the space forward and continue to do. OpenAI has developed a close relationship and partnership with Microsoft, with most services provided by OpenAI also available through Microsoft's cloud offering Azure. This partnership has also resulted in the powering of things like Copilot, found in GitHub, Office Suite, and Bing, etc. This partnership has also resulted in powering the Copilot line of products found in things like GitHub, Office Suite, and Bing from Microsoft. And note, as long as OpenAI continues to lead the innovation within the space, in almost all cases, from here on out, I'm just saying this right now, is that I recommend, and my team recommends, that you stay within the OpenAI ecosystem, unless there's any particularly important reason that you have to go outside of it. Maybe a client wants something outside of the OpenAI ecosystem. They want an open source LLM, but typically people get a lot of shiny object syndrome and they try to jump around and try, but these other models, etc. And the business applications that you're going to build, most cases it's best to stick with OpenAI. We have been dabbling in Anthropic a little bit more with the top of the line models as well. And of course, we have the GPT models from OpenAI, which, while drastically increasing in size and capabilities over each iteration, like GPT 1, 2, 3, and 4, the GPT models are a series of transformer-based models that undergo an assortment of different and proprietary techniques used by OpenAI to be able to create models that understand and generate language. The most widely used and well-known is, of course, the ChatGPT series, which has been tuned using reinforcement learning with human feedback, which we've covered in this video. That's really one of the key things that makes ChatGPT go from the older language model, because GPT-3 was nothing new. It had been around for a few years before ChatGPT came out. And all they'd done was use this reinforcement learning with human feedback and fine-tuning process to turn GPT-3, the language model, into ChatGPT, the conversational assistant, which is really what blew the scene wide open for things like ChatGPT. Then the key products from OpenAI are firstly, of course, ChatGPT, OpenAI's consumer product, the fastest application in history to reach 1 million users, which was just 5 days, and started as a text-to-text chatbot, but has since been stacked with additional capabilities such as image generation with DALL-E 3, web searching with Bing. You've got a code interpreter as well, allowing it to write and run code within ChatGPT. And now we have real-time two-way conversation with audio and visual inputs with the GPT-4o model. And they also have a desktop app for ChatGPT as well. Then we have the GPTs from OpenAI at their OpenAI Dev Day within 2023. OpenAI released these GPTs, their consumer-facing platform for users to build custom versions of ChatGPT that can be shared with friends and colleagues or distributed far and wide through the GPT store, with the promise of future monetization opportunities for the builders on the store. And these custom versions of ChatGPT could be instructed with a mix of custom prompting, custom knowledge, and custom tools as well. So GPTs was a leap forward for allowing people to create their own AIs and their own versions of ChatGPT. Then we have the Assistance API, which is the developer toolkit provided by OpenAI to create GPTs. So to create these custom versions of ChatGPT, you can do it on the ChatGPT website, but you're only able to use it on their site. So the Assistance API is really the developer toolkit underneath that, which allows you to create GPTs that can be used programmatically and therefore be built into your custom applications. So GPTs created on the ChatGPT site can only be used on their platform, but the Assistance API is how we can build them and then deploy them to different parts of the world and different parts of businesses. The Assistance API uses pre-configured helpers for managing things like chat history for the memory, searching for information in the knowledge base, which they call file search, writing and executing code, which is of course the code interpreter, and triggering outside code or APIs using what's known as function calling, which we're going to cover all of this stuff in a later module. The combination of these helpers allows users to create custom versions of ChatGPT for their own specific use case. So here you have a bit of a diagram. We can combine prompting, knowledge, and tools into the GPT builder on the OpenAI site, on the ChatGPT site, of course, and can only be used there. But if you use prompting, knowledge, and tools with the Assistance API, you can put it on places like WhatsApp, on websites, on custom front ends, etc. So that's the two different ways of creating these agent platforms, as we're going to cover later in this course. But these are powerful ways for us to create unique ChatGPT-like experiences. By providing these core elements, you can start to put together complex ChatGPT-like systems in a fraction of the time. The Assistance API requires an LLM to be selected to function as the brain of the system, to control use of these custom functions and knowledge base, and to generate the responses for the users. So this is a really powerful thing that we're going to get into a lot more within this course. This platform that GPTs and the Assistance API provides to be able to create custom ChatGPT-like experiences is something that businesses are really hungry for right now. OpenAI offering this is such a leap forward. For us to create these kind of things before with chat history, file search, code interpreter, function calling, we used to have to create this all ourselves manually, but they've just bundled it all into an Assistance API for us here. Specializing in text-based agent creation with these platforms is a really smart move as well. And then we have some of the other products that OpenAI offers. We have the ChatGPT APIs, embedding models, which you'll understand more after the next video in this module. Speech to text, being able to provide a speech and audio file and get out a transcription, which is done with Whisper. You have text to speech, which if you want to generate an audio file in someone's voice, you have the TTS, text to speech. And we have image generation with DALL-E 3, which is the latest image generation model, which is pretty good by industry standards as well. Then we have Anthropic. So Anthropic was originally formed from disaffected engineers from OpenAI based on directional differences following the partnership between OpenAI and Microsoft. So that partnership really triggered some people to say, hey, this is not what OpenAI was supposed to be. We're going to go and start our own thing, which is some of the best talent in OpenAI has left to create Anthropic, which is why they've grown so fast. So Anthropic puts an increased emphasis on safety in developing foundational large language models, and this has resulted in improvements in the steerability of the models themselves. So Anthropic has released the Claude line of foundational models, whose capabilities closely follow that of OpenAI, and in some instances and situations actually exceed them. I'm using Claude a lot for, even just replacing ChatGPT with Claude. They have their own version of ChatGPT, which is using the model Claude. I've been using that heavily, and I'm actually liking the response a lot more. In many cases now, I see that the Anthropic models can actually be better for at least personal use. Claude's particular strengths lie in its large context length limits, 200K tokens or 350 pages, compared to OpenAI with 128K tokens as of back in May. Anthropic has a partnership agreement with Amazon Web Services or AWS, and it is available through the Bedrock service as well. So Microsoft and OpenAI and Anthropic and Amazon are the two camps at the moment. And the key products we have from Anthropic, mainly Claude, and the 3 different sizes or versions of Claude that they offer. So Haiku, Sonnet, and Opus. This is one that is very good at the moment. Then we have Google, and Google is actually a surprising laggard in the AI race, although they're quickly regaining the lost ground. The fact that Google would be lagging in any event, given its size, is surprising, but it's even more surprising given that researchers at Google actually invented the transformer model itself, which is what all of this LLM frenzy is really built on. So Google has produced its own Gemini suite of models that rival the performance of Claude and ChatGPT. Its most recent and powerful models in this lineup, Pro and Ultra, have an absolutely astonishing 1 million tokens of context available to them, which is 5 times more than the already outstanding context length of Claude. There are also indications that Gemini has defeated the issue of the lost in the middle, or the tendency of models to lose important information as the size of the context window becomes larger, which you will be learning more about in the prompt engineering video of this module. But with that in mind, Google has become its own worst enemy at times, with some less than transparent demos that have overhyped the capabilities of its models, that have dealt significant damage to its trustworthiness. So Google is kind of been tripping over its own feet here for a while, but they are moving in the right direction with their products. So I think we do have a lot of interesting stuff to come out of Google in the near future. Google still has a vast portfolio of productivity tools, the whole Google Docs suite that we're using right now, and Drive, etc., with massive adoption on Docs, Sheets, Chrome, Search, and Android. So it's far too early to be able to discount Google's abilities in the age of generative AI. More so, APIs such as Google Maps are increasingly valuable for all sorts of the agents that we build. So the fact that they have such an extensive suite of really key and powerful APIs, I wouldn't be surprised if they make some massive gains over the coming months and years with the rise of these AI agents. So keep an eye on Google. Key products from Google are the Gemini suite of models. Same deal as Anthropic, where we've got 3 different sizes: Nano, Pro, and Ultra. Then we have Amazon. To most people, Amazon is a trusty online shopping platform that delivers their often unnecessary purchases within 24 hours. I am guilty of that. However, the majority of Amazon profits, actually 74% of them in 2021, come from their cloud services division, Amazon Web Services. So you might think of Amazon as an e-commerce company, but technically they're making majority of their money from their cloud offering and Amazon Web Services. So AWS is the leading player in the market of cloud computing with 32% market share in 2023. Since the release of ChatGPT, Amazon has largely been content to watch the rollout of other models while using its dominant position with AWS to be the hosting platform of choice for the new AI-based applications. So they've got a really good spot where they can just sit back and say, hey, look, all this stuff is coming out, and they're just watching the money roll in, basically. Amazon was also almost the preferred partner with OpenAI instead of Microsoft, but did not want to make the concessions in terms of credits for its cloud services that OpenAI was demanding. Amazon has also made significant strides in providing the Bedrock service, which is a pseudo assistance API service for other model providers to use platforms like Anthropic, Mistral, and Hugging Face. This includes the ability to integrate tools, monitor usage, and crucially, to do so within the confines of an existing line item and integration for many corporations, AWS. So for so many companies that are already paying for AWS, you can just add on to the existing bill and not be creating a whole new platform that they're subscribed to as well. So it slips nicely into the stuff that they're already paying for. As it is available within AWS as well, users gain access to those services and integrations with their Bedrock applications. The key product from Amazon, or AWS specifically, is Bedrock, a fully managed service that provides access to leading AI foundational models through a single API, allowing developers to build and customize generative AI applications easily. Best for businesses and developers looking to integrate advanced AI into their applications without managing the infrastructure, which is the key part here. Then we have Meta, or Meta AI in this case. Obviously the parent company of Facebook, Instagram, and WhatsApp. They are another key player in the AI space, and they've developed the Llama series of models. Meta, as of right now, has dedicated itself towards open source release of each of its models, along with exposing its research. So they're doing what OpenAI said they were going to do, but they're having to pick up the slack here. So it's likely that this trend of openness will decrease considerably as it starts to productize these services within their platforms. However, this commitment to open source has provided a powerful force for pushing the field forward as a whole. And Meta AI is headed by Yann LeCun, a French-American winner of the Turing Award, essentially the Nobel Prize for computer science. And LeCun is considered one of the 3 godfathers of AI. And in short order, he has worked on and guided groundbreaking research in computer vision and transformer technologies and architectures. Meta also has a substantial advantage over its rivals, the sheer volume of GPUs and GPU equivalents for training their models. While the number is inflated, not all GPUs in Meta are actually available for transformer model training, etc. The overwhelming amount of this raw compute means that Meta can attract some of the best talent in the industry. Now, this is ridiculous. If you look at Tesla, Inflection, all these, Google A3, all of these different services and the amount of GPUs that they have, Meta is absolutely stacked with GPUs, which is, in this day and age, is a huge advantage to have. I believe I heard an interview with Mark Zuckerberg and say that, hey, we have a bunch of cash on hand, we have nothing to spend it on. Why don't we just buy a bunch of these because we're going to need it for the metaverse anyway? And then by chance, they ended up being in the perfect situation to capitalize on this AI boom. So this is not something to be overlooked, as having this capability to train models is hugely powerful for these bigger companies. Key products that they have, Llama 3, we've got the 8B model, the smallest one, and 70B, which is the largest model for now. And this is, of course, all subject to change. Mistral AI is a French-based startup that is a contributor to the open source movement, founded by a collection of Meta and Google defecting engineers. It raised an eye-watering amount of money, 113 million for its seed round during the early days of the ChatGPT gold rush. And while initially this investment seemed ridiculously overpriced, Mistral has actually released a steady stream of innovation that is increasingly making evaluation seem like a bargain. Mistral uses a combination of high-quality training, data sources, and architecture to produce world-class models that are a fraction of the size of their competitors. Mistral also struck a partnership agreement with Microsoft and AWS to provide its models to their cloud computing customers. So open source leader to some degree, and they have a ton of money behind them, and they're making very good models. They have Mistral 7B, these smaller ones. We have Mistral 8x7B, which is a mixture of experts model that they have, combine smaller models together to make a more powerful combined one. And then they have Mistral Large as well. So these guys are really someone to keep an eye on and have a play around with some of their models as well as you see them on different platforms. And finally, we have Hugging Face, which is yet another French company in the AI world. But Hugging Face is a unique player in the AI landscape, which serves as a central platform for hosting, sharing, and collaborating on AI models. And while not a model provider itself, Hugging Face has become a crucial hub for the AI community, facilitating the exchange of ideas and fostering innovation in the field as well. So Hugging Face provides model hosting, so you can put your models up there for collaboration. You can find a range of AI models from language to computer vision, etc. There's all these different settings on the side. You can get community feedback because there's so many people active on the community. And you can also do integrations, partner with AWS for easy deployments and stuff like that as well. So it looks like this. You've got your models, data sets, etc. You can come through here and find Meta models, Google ones as well, filter through all these different types of models, text to image, text to speech, etc. So it's a marketplace for models and data sets as well. Now we can get into the key takeaways of this video. So starting off with the types and terminology we've covered. Firstly, artificial intelligence being the umbrella term for techniques that enable machines to perform tasks that typically require human intelligence. So the umbrella term of trying to replace humans in certain tasks. Within artificial intelligence, we have machine learning, a broad category of techniques which enables computers to learn from data and make predictions without being explicitly programmed, which is the key part here, and is a massive leap forward in software and creating programs that are intelligent as this key part here at the end. And then with the machine learning, we have a range of different techniques in order to deal with different situations and different data types. Firstly, supervised learning, using labeled data sets to train a model that understands the relationship between input and output labels. Then we have unsupervised learning, a training approach which is designed to uncover the hidden patterns or structured in unlabeled data. And deep learning, which is a training method specifically focused on the use of artificial neural networks, which is really tailored to more complex types of data. And we have computer vision, which is focused on enabling computers to interpret and understand visual information like humans do, using, in basically all cases, artificial neural networks. So the subset of deep learning is computer vision. Natural language processing, which is aiming to enable computers to understand, interpret, and generate human language. So focused on how can humans and computers interact as seamlessly and smoothly as possible. And finally, we have generative AI, which is a type of AI where we're seeking to generate new and original content by learning patterns from existing data, which is distinct from discriminative AI, or these models where they're only designed, like in most cases of supervised learning, to predict or generate a specific set of outputs. Maybe it has 3 options, or maybe it's expected to generate a price in the case of the housing example. So that's the difference between generative and non-discriminative and discriminative AI. Then we have the Gen AI providers, which are shot through quickly. OpenAI, the world leader in text-based generative AI, offering powerful models like GPT-4, DALL-E, Whisper, etc. And Anthropic, which is a close competitor made up of a considerable amount of OpenAI ex-staff that emphasize on the safety of large language models specifically, when they offer the Claude line of models, and they're partnered up with Amazon. Google, inventor of the Transformer model, offering the Gemini suite of models, which are lagging behind, but quickly catching up and have a lot of potential to really dominate the space over the coming years. Amazon, they are focusing on being the cloud hosting provider for all of these AI applications which are being built through Amazon Web Services, and they also have their Bedrock service to get in the mix as well. Then we have Meta, and specifically the AI department, and they're developing the open source Llama series of models, and they also have a substantial advantage in computing power for training new models. They also have an incredible set of options for distribution through WhatsApp, Instagram, Facebook, all of these different platforms to integrate AI features throughout. So For us, we will be looking very closely at that over the coming months and years as to how we can tap into the market of AI solutions within the Meta ecosystem as well. The Mistral is a French-based startup producing world-class models that are the fraction of the size of their competitors, and they are a really open source player to watch here. And finally, Hugging Face, which is really a unique platform for hosting, sharing, and collaborating on AI models, serving as a crucial hub for the AI community. And that is all we have for the AI landscape. I hope that's been helpful for you to understand what this space currently is, the different types of training methods, what AI actually is, and what we're trying to do with this technology. That should be a very good base for you to go into the next video in this module, which is going to be LLM theory, where we're diving deeper into neural networks, how they're trained, all of the different components of it, the transformer architecture, and really going deep on tokens, embeddings, and all of the fancy jargon that you're going to hear floating around in the space. So this has just been an introduction really to the rest of this module. I hope you're ready for the next one and come prepared because we have a lot to get through. So I will see you in LLM theory.